Hello, I'm Sam, and this is my lab report for Lab 1, Constant Velocity for Physics 2211. The purpose of this lab was to explore the application of Newton's second law in analyzing the motion of an object moving at a constant speed without changing direction using both experimental and computational models. This lab was successful in creating both experimental and computational models that match well with each other, as well as agreeing with Newton's second law that force is equal to mass times acceleration, so when you set acceleration equal to 0, then the net force acting on the object is also 0. So first, some assumptions. We're assuming that both the frictional force and the area resistance are negligible, and that the ground is completely flat and perpendicular to the direction of gravity. So first, we know that Newton's law states that the net force is equal to mass times acceleration. So if we set the acceleration to 0 meters per second squared, then the net force is also 0. We also know through the momentum principle that the net force is equal to the time derivative of momentum. So in the case where the net force is 0, that time derivative is also 0, so there is no change in the momentum. So by plugging everything together, we then obtain that when the acceleration is 0, then the net force is 0, as well as there is no change in its momentum or velocity. So in my experimental model, I started with a basketball as well as a camera. The motion of the basketball is perpendicular to the direction in which the camera was recording, and all of this is on a solid floor with tiles to kind of help me with direction. So this is the recording that I took for this experiment, and I also used some video editing techniques to make the colors more contrasting so it can be used better for tracker analysis. I first used tracker to do a distance calibration with the diameter being 0.239 meters and implemented the X and Y axis on tracker. Then I used auto tracker to track the position of the basketball. Specifically, the center of the basketball is what I tracked inside my data, and this is the data that I obtained. And you can see first through figure 1 that this is the x values of the center of the ball over time. It is a relatively straight line with a positive slope. And we can see here this is the y values of the center of the ball over time. You can see it's a relatively flat line across the time. So moving on to my computational model, the initial conditions I chose is this. So I set the initial condition at the x value at the first frame, y value being the radius and z being 0. The initial velocity is calculated by doing delta x over delta t over the first two frames, and yeah. So through our code, I just implemented the values I obtained for our initial position into the code. So here are the specific points I had that are marked inside red. And ultimately, I obtained this graph of the ball's x position over time. So if we compare the experimental model as well as the computational model, the experimental being blue and the computational being red, we can find several things. So the first thing is that we can see that these two graphs match quite well with each other, and that the velocity of the ball's center of mass is almost completely constant, with the ball following basically a perfect straight trend line with r squared equal to basically 1. And that both the experimental and the computational models show the ball traveling at a very relatively constant velocity. So this agrees with the theoretical model that when there is no net force acting on the ball, there is no change in velocity. Additionally, we also find that the y value of the ball's center of mass over time remains relatively close, but sometimes might deviate slightly. This might be due to inaccuracies from the auto tracker, and that the computational model underpredicts the x displacement of the ball's center of mass over time, which might suggest that the auto tracker underestimates the distance traveled by the ball in the first two frames, or that the ground might not be perfectly flat. So these two issues both might contribute as sources of error. So the discussion I had was first, if the axes were flipped, we can see that when they're flipped, there will be several different results, such as like changing the slope or changing the axis or needing some other types of external forces to make sure that the net force would be equal to 0. And we can also find that what forces are added together to give the net force equal to 0, which in this case would simply be that the net force is equal to the summation of all forces, which is equal to the force of gravity plus the normal force. And from this, because we know that the net force is 0, we can therefore find out that the normal force is basically equal to negative force gravity. And another interesting thing to discuss is just that an object that is not at motion with a velocity at equal to 0 is also at constant velocity, and there will also be a net force of 0 on the object until it starts accelerating. So the conclusions that I can draw from this is that I was able to create a controlled experimental setup, computational model, theoretical model, and good experimental verification. The experimental and computational models agree well with the theoretical model using Newton's second law, and certain sources of error might arise from neglecting air resistance, friction, the floor might not be completely flat, as well as certain software imperfections. So these are my references, and this is it to the lab report. Thank you for listening.